Morning.
Good morning. All right, give everybody a little bit to get in, situated. All right. Good morning, everybody. Guess we will jump right in. I guess first, actually, a reminder, this Friday is Good Friday, and so we will not be having class. So yeah, feel free to use that time, catch up on homework, catch up on sleep, do whatever it is you need to do. Just stay safe. Go ahead and put it in the chat. All right. Okay, so last time we ended up getting into this idea of some parent functions. And this is a list of all of the main functions that we would deal with in this class. So we have what's called a constant function, which is just a horizontal line. We have a linear function, which the parent function is just f of x equals x, the simplest version of y equals mx plus b. And we have the absolute value function, where the function just equals the absolute value of x. Looks like this. It's basically the same thing as this one, except this line down here gets flipped up, makes it look like a V. You have the square root function and the square function, cubic, and these three are kind of related as well, where you could say that the starting point is kind of this x squared function, and the x cubed function takes this left arm and flips it down below the axis. And this square root function is kind of like just one arm of this squared function, but it goes this way instead of up. We have the reciprocal function, 1 over x, and then this one that we talked about last time, the greatest integer function, also known as the step function. Yeah, so this is just a quick rehash of the parent functions. And what we're going to do today is start in with how do we take parent functions and make new functions. So let's look at that. Let's get up our basic kind of graph here. Let's say we have our simplified function. Y equals x. All right. So we want to know what can we do to this line. And we'll get into the algebra of it a little bit later. But we want to actually know what ways could we move or change this line in order to make a different line. So pretend that this is actually like a physical thing that you can pick up and do something with. What could I do to it?
You could find the intercepts.
What? I didn't hear you.
Like, could you find the intercepts, like the x and y?
You're thinking about it in algebra math terms. We're trying to start with non-mathy terms and move into the math of it. But yeah, so think about this as like a physical thing. It's like a little blue piece of wood. What can you do to that? think about it as a ruler. I know it's hard to see this ruler because it's plastic, invisible. Think about it, that blue line is actually just a ruler laying on a table. What can you do to it? Try and think as the answer almost sounds like a really dumb answer, but I promise you it's not. There's a ruler sitting on the table.
Measuring.
What?
Measuring.
So yes, if it was a ruler, but that's just because this is the only thing I had that kind of looked like that. Imagine it's a long marker or something. It's a thing. I liked a stick because that's the kind of what it is. It's just a blue stick. What could you do to a stick sitting on the table? Some of you might have cats. What do cats like to do to stuff that's sitting on places? Or really animals in general, but especially cats.
Knock it down.
Okay, knock it down, but in order to knock it off the table, what do they have to do first?
Move it around.
Move it around.
Oh.
Yes. They have to move it. So the simplest thing that you could do with this stick is you could move it. You can move it up. All right, my assignment this weekend is going to be get new markers. You could push it up. You could push it down. You could push it to the side. Push it to the left. So the first thing that we're going to learn about in our list of what we call so shifts or slides. The other word that they use that's the fancy math word is translation. So this is as simple as these first transformations are as simple as moving the thing around. So in the example that I drew up here, we could push the whole thing up, or we could push the whole thing to the right. Again, I know my penmanship isn't great. Sorry about that. Or we could push it left, or we could push it down. Those are the four directions that we can move. Okay. So let's look at what happens to every point on this line when we move it. So let's say that we're moving it up. And how far up do we want to move it? Just give me a number.
Seven.
Okay. So this is up 7. All right. So let's look at this. Assuming that this point is, let's say, 2, 5. This point is 6, I don't know, 10. And we move it up 7. What we're doing is we're moving every point up 7. So what are the new coordinates? What do you do to a point if you move it up 7? What does it mean to be at point 2, 5? How would we find that point?
2 on the x-axis and 5 on the y.
Okay. So what direction is the x-axis? The positive x-axis. Which one is the x-axis?
The
Here.
horizontal.
Yeah, so this one is the x. Which way is positive x?
The one going up and down.
To the right.
To the right. So if you go positive, if you increase your x-axis, your x component, you're going to the right. If you decrease it, you're going to the left. Same is true for up and down. Up and down is makes a little bit more sense because we generally think of up as positive and down as negative. Just remember that it's a right-hand person's world. So you go to the right, it's positive. You go to the left, it's negative. So if you go up by 7, what coordinate determines up or down?
The second one.
Y, the second one, yeah. And up means what about the second one? Is it
Positive.
is positive. So if you go up by 7, you were at 2, 5. You didn't go left to right, so the 2 stays the same. What happens to the 5?
You said it goes up by 7?
It goes up by 7. So the new coordinate is 7 higher than the old one, which would be what?
12.
What?
12.
12. Okay, now apply the same logic to this point.
Well, 6 stays the same.
6 stays the same.
And 10 will turn into 17.
and turns into 17. That is correct. So this is true for every point, because remember, a line is made up of a bunch of different points. So if you shift up, then every point has 7 more added to it. Okay? Every y coordinate has 7 more. Okay? Well, what if we went down? What if we were going from the green line down to the black one? That means we're going down by 7. Well, what happens if we go down by 7? Every y coordinate loses 7. Okay? All right. So what about left to right? What if we shift this line to the right by 3? And I know it's probably not to scale, it's fine. Just go with it. Well, what happens to the coordinates? What happens?
Well, the y value stays the same and the x changes.
The y value stays the same and the x changes. Okay. So then our coordinates would be something 5 and something 10. What happens to the x value? So
It has been okay, so it'll be like -1, 5, and 3, 10.
So we're going to the right. Right is what direction for x?
Positive.
Positive. So the right is going to have 3 more for every point. So what happens to the 2? It doesn't become -1. That would be going to the left. What?
It's gonna be 5.
It's going to be 5.
The next one is gonna be 9.
So we go to the right. X gets 3. And if we went to the left, x loses 3. Okay. So this is what's happening to the points specifically. Now I'm probably about to say something that may upset some of y'all, but just go with it, because this idea is actually very, very it's weird to think of at first, but it's very, very helpful in understanding what to actually do. Because it's kind of backwards from this. So what we do to make this stuff happen to the parent function is actually the opposite of what it looks like we're going to do. And I'll show you what this means and how. But let's see. So I have a black and a red marker. And they are right next to each other. So pretend for a second that nothing existed in the entire universe except for you and the black and the red marker. You turn around and you look somewhere else because you thought you might have heard something. And then you turn back around and you don't see this, you see this. My question to you is, which one of them moved? So again, it's kind of weird to think about. You have two different objects, and you look away, and suddenly those two objects look like this. So start, end. Which one of them moved?
Black.
Why do you think the black one moved? Okay, so this is weird. So just don't be afraid of giving a wrong answer, especially right now, because it's very different from what you are commonly used to thinking. So you have to think through it in order to really get it. So that's why I want to know what you're thinking. I don't care how silly you think it sounds, just go with it. So why do you think the black one moved?
Mainly because the red one, I'm thinking of it like it's just on a graph, so it looks like the red point didn't move, but the black one did.
Okay, so if it's on a graph, it looks like the red point moved, but the black point didn't. What I'm actually talking about is one of these things is the line, and one of them is the graph paper. The graph, the axes that are underneath that line. So they're not 2 points on a graph. One of them is the graph itself, and the other one is the line, or you could even say a point if you want to. So why do you think the black one moved?
Wait, hold on. Which one is the graph?
We'll say the black one is the graph paper, and the red one is the line on that graph paper. So maybe, I don't know, it'd be helpful if you saw them like this first. And then I said, okay, you turn back around, which one moved? The way I do this in class is actually with boxes. Maybe we can use something a little different. So let's imagine you have these two squares. They're sitting on top of each other. And you turn around and suddenly they're like this. Which square moved? They were like this. You saw them like this. So you want to say that the green one moved, right? Right?
I kind of think the orange one moved.
I'm physically moving the green one if you see it, right?
Yeah, but wouldn't that mean I mean the orange one moved because you can move the orange one without moving it, but you can show that the triangle one is moving, even though I said it's like the
So,
triangle is staying in place, but the circle's moving.
so the orange one moved on this case, and then they were next to each other. The green one moved in this case, and they were next to each other. They both moved in this case, and now they're next to each other. But the only thing that you can see in the entire universe is the two squares, is the two colored things. So you can't actually tell which one moved. And even if you're watching it out in the middle of nowhere, you can't really tell which one moved because you don't have anything, what's called a context clue. There's nothing behind them. Like me, I'm not moving. So you know that if they start like this and they end like this, you know the orange one moved because I didn't move. So you have a context clue. But the point is, you could move this one to the right or this one to the left. And it would be correct because now they're this far apart when they were this far apart. So this brings us to what you're supposed to do with all of these transformations we're going to be getting into the next week. Think about whatever you want to do, and then algebraically, you need to do the opposite to the graph paper. Sounds really bizarre, but go with me. So if you move the line up, it looks the same as if you move the graph paper underneath it down. And this is something that is very difficult to do without my my smartboard, so I'll have to come up with a good visual explanation of it, finding some good graphing software or something. But moving the stick up on the graph would be the same thing as moving the graph paper underneath it down. Or vice versa. If you move the stick down on the graph, it would be the same as if you moved the graph paper underneath it up. And this is how we actually do these transformations algebraically. So to slide something up, so we'll call this if you want to go up by some number C, what you're actually doing is moving the graph paper underneath it down by C. When you do that, you're moving all of the Y values down by C. So what we do is, in our equation, we take everywhere we see a y, and we replace it with y minus c. If we go down by c, that's the same thing as moving the graph paper underneath it up by c. So we take our y values and we convert them to y plus c with right by c. We're moving x to x minus c. And if we go to the left by c, that is x to x plus c. So it seems very contrived, very kind of ridiculous, but it becomes especially important when we get into transformations that aren't just easy shifts. So let's actually do one of these. Let's take y equals x. And let's say we moved it up by 3. What is the equation for this green line? So what's the slope of the green line if it's parallel to the black one? Two things are parallel. What is true about their slopes?
It's the same.
It's the same. So the slope was 1. It is now 1. So what is the y-intercept? Of the green one? It's 3.
3.
So x plus 3. So this is the equation after it's been upped by 3. And we're probably about to die out, so we'll go through this example, I guess, on Monday. So you guys have a fabulous